Topic 1, Lesson 1, Wave Properties, found on pages 4 to 11 in your textbook. As always, we're going to start with the connected. So, read the caption and then label the photos with different types of waves that are indicated in some way by the photos. Alright, World of Waves, Figure 1 caption reads, a tsunameter is a buoy anchored to the ocean floor. It detects extremely large waves called tsunamis and sends a radio signal to warn people. So, how is Earth dependent on the sun for energy, and how is a tsunami warning system a benefit to society? Alright, so first we're going to draw those labels. So, the different kinds of waves that are indicated in some way by the photos. So electromagnetic radiation are waves that come from these areas at the top, and mechanical waves are the actual ocean waves, and those are what you can see in the water. So how is Earth dependent on the sun for energy? Sunlight is the primary source of energy for many processes on Earth, such as photosynthesis. The sun also provides the heat that many species need for survival. And how is a tsunami warning system a benefit to society? It can alert people on shore that large, dangerous waves may be heading their way. Then people can evacuate or take shelter. Types of waves. So a wave is any disturbance that transfers energy from place to place. Waves can be classified by how energy is transmitted. Mechanical wave is a wave that moves through some type of matter. Examples are ocean waves and sound waves. Medium is the matter a wave travels through. And vacuum is a mechanical wave. A vacuum is pertinent because a mechanical wave cannot travel through a vacuum, such as space. A vacuum is completely empty. Why is the space around you not considered a vacuum? And that's because it's not completely empty. There's air, there's items, there's all kinds of things. Types of waves. Electromagnetic wave is a type of wave that transfers electromagnetic radiation, a type of transfer energy like mechanical waves, but can travel without a medium. Electromagnetic waves travel through empty space. Examples of electromagnetic radiation include visible light, radio waves, X-rays, and microwaves. Both types of waves involve a transfer of energy without a transfer of matter. While mechanical waves travel through matter, the waves themselves do not move the matter to a new place. Transverse waves. Waves can be classified by how the particles in a disturbance vibrate. A mechanical wave begins when a source of energy causes a medium to vibrate. The direction of the vibration determines what type of mechanical wave is produced. Mechanical and electromagnetic waves can be transverse waves. A transverse wave travels perpendicular or at right angles to the direction of the source's motion. So transverse waves use arrows to indicate the direction the rope is vibrating and the direction energy is flowing. Label a crest and a trough and indicate the amplitude. So a crest is the high point of a wave. A trough is the low point of a wave. Resting position is halfway between the crest and trough. And amplitude is the distance between the highest crest and the resting position. Marks the wave's amplitude. In general, the amplitude of a wave is the maximum distance the medium vibrates from the rest position. So when we're labeling, amplitude is that measurement from the highest crest point and to where it meets at the resting, so that height there. Then we also have to label the crest, which is that top the big hump, the trough, which is the low, the valley. Direction of vibration of motion is going up and down, and the direction of energy flow is moving towards the right where the ropes are being moved. Longitudinal waves. A longitudinal wave is a wave that travels in the same direction as the vibrations that produce it. Sound is a longitudinal wave. Sound travels from speakers when flat surfaces inside the speakers vibrate in and out, compressing and expanding the air next to them. Figure 3 shows a longitudinal wave in a spring toy. When the left hand pulls on the toy, the result is a series of stretches and compressions. Gaps between compressions are called rarefactions. Wave energy moves to the right along the toy, but each spring particle moves back and forth. So figure 3, longitudinal wave, label a compression and a rarefaction. So the rarefaction is going to be this at the beginning where it's being pulled. The compression is where it is being compacted or pushed together. Surface waves. Surface waves are combinations of transverse and longitudinal waves. For example, an ocean wave travels at the surface of water. When a wave passes through water, the water and anything on it vibrates up and down. The water also moves back and forth slightly in the direction that the wave is traveling. The up and down and back and forth movements combine to make each particle of water move in a circle, as shown in figure 4. All right, figure 4, surface wave. As waves move from left to right, they cause the ball to move in a circle. So it's kind of stuck in that one location, goes up, or goes back, comes up, falls back, and then repeats the whole process again. Just going in a circle. Reading check. What is the main difference between surface wave and longitudinal waves? Particles in a surface wave move in 2 directions, while particles in a longitudinal wave move in just one direction. Properties of waves and amplitude. Amplitude is the distance between the highest crest and the resting position. It marks the wave's amplitude. In general, the amplitude of a wave is the maximum distance the medium vibrates from the resting position. So here at the bottom, we have wave A, wave B, and wave C, and we can see that the amplitude increases because that red dotted line is going to be the resting position. And your amplitude is the distance from the resting position at that red line to where the boat is. And we can see that as the different wave variations move down, the amplitude increases. Of these two, which wave has the greater amplitude, yellow or blue? And we can see, based on what I said with the boats, that yellow has the greater amplitude. Properties of waves and wavelength. Wavelength is determined by the distance a wave travels before it starts to repeat. Transverse wavelength is the distance from crest to crest, and longitudinal wavelength is the distance from one compression to the next. So, we can tell wave A, so from where the boat is to where the next crest up is, that's one wavelength. And we can tell that wave A has a longer wavelength that takes a longer amount of time to get from one to the next than does wave D. One yellow wave passes by this point each second, so the frequency of the yellow wave, just kidding, we're going to do that in a minute. Properties of waves and frequency. So frequency is the number of times a wave repeats in a given amount of time. You can also think of frequency as the number of waves that pass a given point in a certain amount of time. For example, if you make waves on a rope so that one wave passes by a point every second, the frequency is 1 wave per second. The greater the frequency, the shorter the wave. The smaller the frequency, the longer the wave. So you can see high frequency with the little short waves, low frequency with the long waves. Frequency is measured in units called hertz. A wave that occurs every second has a frequency of 1 hertz. If 2 waves pass by in a second, the frequency is 2 hertz. So now, 1 yellow wave passes by this point each second, so the frequency of the yellow wave is 1 hertz. 2 green waves pass by this point each second, so the frequency of the green wave is 2 hertz, like we just said up there. Properties of waves. Speed is determined by the distance a wave travels in a certain amount of time. Different waves have different speeds. For instance, a light wave travels almost 1,000,000 times faster than a sound wave travels through air. Waves also travel at different speeds through different materials. For example, light travels faster through water than through glass. Sound travels more than 3 times faster through water than through air. To calculate a wave's speed, divide the distance it travels by the time it takes to travel that distance. So speed equals distance over time. You can also find a wave speed if you know its wavelength and frequency. Just multiply wavelength times frequency. So wave speed equals wavelength times frequency. Reading check. If you and a friend are standing at opposite ends of a gymnasium and one of you claps, will the other person hear the clap at the same time she sees it happen? Why or why not? And no, because it takes more time for sound to reach our ears than for the light from the event to travel to our eyes. Wave energy. So waves transmit energy from place to place. The amount of energy they transmit depends on how much energy was input by the original source of the vibration. Waves that transmit more energy have greater frequency, or faster vibrations, and larger amplitude. Like other forms of energy, a wave's energy is measured in units called joules. In mathematical terms, a wave's energy is directly proportional to frequency. When the frequency of the wave doubles, the energy also doubles. So if you shake a rope up and down twice as fast, you transmit twice as much energy down the length of the rope. Mathematically, a wave's energy is also proportional to the square of its amplitude. For instance, if you shake a rope to make waves and then move your hands 3 times as high with each shake, the wave energy increases by a factor of 3 times 3, or 9. Wave energy key point. So amplitude, higher amplitude equals higher energy, lower amplitude equals lower energy. Higher frequency equals shorter wavelength, which also equals higher energy. Lower frequency equals longer wavelength, which equals lower energy. Math toolbox. The table shows the properties of the waves near the beach on one summer day. Use the relationship between speed, wavelength, and frequency to complete the table, then answer the questions. All right, so first we need to find speed. And to find speed, we would have wavelength times frequency. So 10 times 2 equals 20 meters per second. Then we're looking for wavelength. We can do the opposite, 32 divided by 4, which would be 8 meters. For speed, we can do 36 divided by 12, which is going to be 3 hertz. Then answering our questions, what would happen to the energy of the 10 AM wave if the frequency increased to 6 hertz? And the wave energy would triple. If the amplitude of the 6 PM wave increased to 0.6 meters, how many times greater would the energy become? And the energy would become 4 times greater because it increased. Lastly, recall that speed equals wavelength times frequency. Assuming that the wavelength of a wave stays the same, Would the energy of the wave increase or decrease if the speed of the wave increases? Why? The energy would increase. Increasing speed while keeping wavelength the same would result in an increase of frequency, and increasing frequency increases energy. All right, now we're at the lesson check. So 1, how can you measure the wavelength of a longitudinal wave? And you can measure the distance from one compression to the next. 2, a sound's wave frequency is 4 hertz and its wavelength is 8 meters. What is the wave speed? So 8 times 4 equals 32 meters per second. 3, draw a model of a transverse wave. Use lines and labels to show the amplitude and wavelength of the wave. So you guys should show a wave and appropriate labels for wave's amplitude and wavelength, and you need to draw that independently. 4, during high tide, ocean waves often become larger. If the amplitude of a wave increases by a factor of 4, by how much does the energy increase? Energy is proportional to amplitude squared. So 4 squared equals 16, so it increases by a factor of 16. Lastly, 5. If a musician increases the wavelength of the sound waves she produces without changing their speed, what must happen to the frequency? Explain your answer. It must be decreasing. Speed equals wavelength times frequency. So if the speed stays the same despite an increased wavelength, the frequency must be reduced. And that ends lesson 1 notes.